Verify the line integral and surface integral of Stokes' theorem for the following vector field, the surface, and the closed curve C. And we're going to assume that C has a counterclockwise orientation and that the surface is consistent with this orientation. So, what are we being asked to do? We are being asked to verify Stokes' theorem. So we need to first compute the vector line integral over the closed curve C of the vector field dotted with that differential d vector r. So that's part 1. And then in part 2, we want to show that this is equivalent by computing the double integral over the surface of the curl of this vector field dotted with the normal vector integrated with respect to the surface. So this is a 2-part question. So to get us started, let's just think about the sketch of this surface and curve. So what is our surface here? The surface S is the upper half of the sphere, x squared plus y squared plus z squared equals 9. And C is the circle, x squared plus y squared equals 9 in the xy plane. So we have a hemisphere. So let's start by sketching this. So I'm going to sketch a full circle to get us started. And again, we know that we're only thinking about the portion of the sphere above the xy plane. So here is our surface S. And then below is that boundary curve C, our oriented curve C, oriented in that counterclockwise direction. And so we are thinking about this surface S. All right, so we can incorporate in our axes here. So we have the z-axis. We have the x-axis and the y-axis. Okie dokie. So we also want to note here that our sphere has a radius of 3. So we'll be sure to indicate this on our graph. And so the first thing that we need to do is to compute the vector line integral. So we want to compute that vector line integral over this closed curve C of the vector field dotted with that differential d vector r. And we know for computation purposes that we rewrite this as the vector line integral over C of the parameterized vector field dotted with the tangent vector dt. So we need to find a parametric description for C. And so to do this, let's recall that for a circle, x squared plus y squared equals r squared for our radius, we know that a one-parameter description of a circle is defined as x of t being equal to r times cosine of t, that the y component would be y of t is equal to r sine of t. And what would a z component be for a circle in the plane? 0. So we have z of t can be 0 because we're in the plane. So keeping in mind that we have a radius of 3, we can find a parametric representation for our curve C. So C again is x squared plus y squared is equal to 9 with a radius of 3. And again, I should have included this up here with our parametric representation. Don't forget your bounds. So this is such that t is greater than or equal to 0, less than or equal to 2 pi, because we're thinking about a full circle. So our parametric representation for this circle, vector r of t, is defined by the components x of t, y of t, z of t. And since our radius is 3, the x component will be 3 cosine of t. The y component will be 3 sine of t. And the z component is 0. And this is such that t is greater than or equal to 0, less than or equal to 2 pi. So there you have it. Where we have it. There we have it. There is our one parameter description of the curve C. So we now need to use this to parameterize our vector field. And we need to use this to find the tangent vector. So let's parameterize our vector field first, since we have r of t here. Let's note that we are given a vector field. Capital F is defined as y minus x 10. So we're now going to go ahead and parameterize this in terms of those components we just defined. So we can say that the parameterized vector field, capital vector F, of vector rt is going to be equal to y of t minus x of t 10. And plugging these new components in, this will be 3 sine of t minus 3 cosine of t 10. So now the last thing that we need to do is find the tangent vector. So again, we're just differentiating what we found above. So r prime of t is going to be equal to the derivative of 3 cosine of t is minus 3 sine of t. We have the derivative of 3 sine of t will leave us with 3 cosine of t. And the derivative of 0 is 0. And for simplicity here, I'm going to factor out that greatest common factor of 3. So I have 3 multiplied by minus sine of t. 3, we factored that 3 out, so this will be cosine of t, 0. So the hard work is over. We have the parameterized vector field and we have the tangent vector. So we're ready to evaluate the vector line integral. So again, that's the vector line integral over the closed curve C of the vector field dotted with that differential d vector r, which for computation purposes we have converted to the vector line integral over the closed curve C of the parameterized vector field dotted with the tangent vector dt. So plugging in everything that we just found, we have the integral from 0 to 2 pi of our parameterized vector field, which is 3 sine of t minus 3 cosine of t 10. And we are dotting this with 3 multiplied by the vector minus sine of t cosine of t 0 dt. So here we go. I'm going to take this 3 to the outside of our integral. So this is 3 times the integral from 0 to 2 pi of minus 3 sine of t squared. Then we have minus 3 cosine of t squared plus 0 dt. And we'll give ourselves a little more room. So notice between these first two terms that we have a greatest common factor of negative 3. So let's pull that out, which leaves us with negative 9 times the integral from 0 to 2 pi of sine squared of t plus cosine squared of t dt, which we're so excited we know that that is Pythagorean's theorem. So this just goes to 1, leaving us with the integral of negative 9 times the integral from 0 to 2 pi dt. So this simply integrates to negative 9t from 0 to 2 pi, which leaves us with a beautiful final answer of negative 18 pi. So we have calculated the vector line integral of Stokes' theorem. And now to verify this, we want to go ahead and compute the surface integral. So let's take a look. So in part 2, we need to verify that the double integral over our surface f of the dot product of the curl of the vector field and the normal vector field is also going to be equal to negative 18 pi that we just found with the vector line integral. So let's keep in mind here that we're given the vector field f defined by the components y, negative x 10, and we are given the surface S that is defined as the hemisphere above the xy plane. So looking at our surface integral here, we need to compute the curl of the vector field And then we also need to find the normal vector for the standard parameterization of a sphere, here specifically with a radius of 3. So I'm going to start by computing the curl. So let's compute the curl of the vector field, which again is the del operator crossed with the vector field. So here we go. The curl of this vector field is going to be equal to that del operator. So we have the vector ddx, ddy, and ddz. And we again are crossing this with this given vector field y minus x 10. So if it helps to see this easier, we can put this into the determinant of that 3 by 3 matrix. So you have the unit vectors, and we have ddx, ddy, ddz. And then our third row is our vector field, y minus x 10. And computing the determinant, we see our first component, we have 0 minus 0, I hat, minus, we then have 0 minus 0, j hat, plus, then we have minus 1, k hat. So this simply leaves us with negative 2, k hat. And so our normal vector, we can leave it like that, there's nothing wrong. Excuse me, not our normal vector, the curl of this vector field, we can either simply leave as negative 2, k hat, or write it in the component form 0, 0, minus 2. All right, so now that we have the curl, we need to define or find the normal vector. And so to do this, we're going to need to go ahead and recall the standard 2-parameter description for a sphere. So let's recall that if we let u define phi, and if we let v define theta, then the 2-parameter description R of uv has the components, the parameterized components, x of uv, y of uv, z of uv. And keeping in mind those spherical coordinate conversions, we know that the parameterized x component will be rho sine of phi cosine of, well, we should say not sine of phi, this should be sine of u cosine of v. The parameterized y component will be rho times sine of u sine of v. And the parameterized z component will be rho cosine of u. And this, of course, is such that u is greater than or equal to 0, less than or equal to pi, and v is greater than or equal to 0, less than or equal to 2 pi. And so for this standard parameterization, remember that the normal vector is defined as the magnitude of the cross product of the tangent vector in the u direction and the tangent vector in the v direction. And this is defined as rho squared times sine squared of u cosine of v. The second component is rho squared sine squared of u sine of v. And then last but not least, we have the component rho squared sine of u cosine of u. Okay, so this is the general parametric description for the general 2-parameter description for a sphere. Now we just want to be careful here. We are working with a hemisphere. So S is the hemisphere defined as x squared plus y squared plus z squared is equal to 9. And this is such that z is greater than or equal to 0. So a couple of notes to get us started here. We know that rho is equal to 3, our radius. And then the other thing I want you to notice that since z is greater than 0, this is going to change those phi bounds or our u bounds. So We can even make a note here just so we don't forget that u, right, the angle from the positive z-axis to rho is restricted to above the xy plane. So that's u is greater than or equal to 0, less than or equal to 2 pi. And we have that full circle for theta, so we have that v is greater than or equal to 0, less than or equal to 2 pi. And so we now want to define the normal vector specific to our given rho. So the normal vector here for our hemisphere is defined as 9 times sine squared of u cosine of v. We have 9 sine squared of u sine of v. And last but not least, we have 9 sine of u cosine of u. All right, so we have our normal vector and the bounds needed for our surface integral, as well as the curl. So we have everything we need now to compute the surface integral. So we want to evaluate that surface integral of Stokes' theorem. So that is the double integral over the surface S of the curl of our vector field dotted with the normal vector ds. So we're integrating here with respect to our surface area. So let's plug in what we found. This is the integral from 0 to 2 pi. We then have the integral from 0 to pi by 2 of our curl, which is 0, 0, minus 2, and we're dotting this with the normal vector. So this is 9 sine squared of u cosine of v, 9 sine squared of u sine of v, and then we have 9 sine of u cosine, there's no comma there, that's 9 sine of u multiplied by cosine of u d. We need a little more room. So we have the order of integration here is going to be du dv. Phew. So we're ready now to actually go ahead and compute this. So giving ourselves plenty of room. And notice, while this looks kind of nasty when we first write it, the first two components of the curl are 0. So when we compute the dot product, look at what happens. We have the integral from 0 to 2 pi, the integral from 0 to pi by 2 of 0 plus 0, and then we have minus 18 sine of u cosine of u. Woohoo! Du dv. So look at how lovely that is. And I'm going to rewrite this as negative 9. So I'm factoring a 9 out of this, or a negative 9 out. So minus 9 times the integral from 0 to 2 pi, the integral from 0 to pi by 2, and what's left is 2 sine of u cosine of u du dv. Now you may be asking yourself, well, why did you do that? Well, I don't want to use u substitution, and this is the double angle formula. Woohoo! And so we can rewrite this now as the cute compact integral negative 9 times the integral from 0 to 2 pi, the integral from 0 to pi by 2 of sine of 2u du dv. And so this is a general antiderivative. This becomes negative 9 times the integral from 0 to 2 pi of minus cosine of 2u by 2, which we'll evaluate now from 0 to pi by 2 dv. So I'm bringing all those constants to the outside. So this is 9 halves times the integral from 0 to 2 pi of, so we have cosine of 2 times pi by 2, so this just leaves us with cosine of pi, minus cosine of 0. And let's bring this up for more room. And don't forget your dv, shame on me. So we can evaluate, we have cosine of pi, we of course know goes to negative 1. Cosine of 0 is 1. And this leaves us with 9 halves times the integral from 0 to 2 pi of negative 2 dv. So those 2's will cancel each other out, leaving us with negative 9 times the integral from 0 to 2 pi dv, which simply integrates, so this looks familiar, we have negative 9t from 0 to 2 pi, which leaves us with that beautiful final answer and confirms Stokes' theorem. We have negative 18 pi. Woohoo! So we have officially confirmed that the vector line integral over the closed curve C of the vector field dotted with that differential d vector r is equal to negative 18 pi, which also equals the double integral over the surface S of the curl of the vector field dotted with the normal vector integrated with respect to the surface.